So we'll cover this chapter 1 of this booklet, Introduction and Equilibrium Solutions. So we're first going to look at constant absolute rates of change, constant relative rates of change, and then we're going to get into equilibrium solutions of differential equations or qualitative analysis of those differential equations, because qualitative analysis allows you to understand the long-term behavior of a differential equation without actually solving it, because sometimes they're very difficult to solve. Okay, so let's get started. So scroll down to the relevant section where we see the introduction. All right, so what is a differential equation? An ordinary differential equation, or ODE for short, is an equation that involves rates of change. For example, if we have dy on dt equals a constant, you might view that as, say, the rate at which water pours out of a container into something else, and say that's 3 liters per minute, for example, right? Then you could model that situation with a differential equation, dy on dt equals 3. Okay, and the goal here is to solve that differential equation for y as a function of t, so that you can model how, say, the water moves out of the container as how it depends on time. Okay, so let's get back to the document here. An equation involving rates of change with ordinary derivatives. For example, dy on dt rather than partial derivatives, partial y on partial t. Remember, partial derivatives are those derivatives that take all other variables as constants when you differentiate them. So it only takes into account what's on the bottom of that symbol there, as to how that variable varies with respect to that variable, and it treats all other letters as constants. So we're in the first half, we'll be mostly interested in ordinary derivatives and equations involving ordinary derivatives, so ODEs. Often problems in mathematics, science, engineering, and it doesn't stop there, right? So chemistry, biology, even economics, and other situations, anything that involves a rate of change can often be described with a differential equation. Now, in this example here that I have on the left, that's a differential equation that relates to some particular electrical circuit where we have a resistance, and that's usually a constant. We have a charge, and we want to know here how the charge varies over time. But what we have is a relationship between the rate at which the charge changes with respect to time and other constants in that circuit. For example, resistance, capacitance, and the voltage supplied by the battery. And then here, again, we have a Q for the charge. So all the other letters are constants in that equation. And if we look through here, it says, well, if, for example, the resistance is 5 ohms, the capacitance is 0.05 farads, and the battery supplies 60 volts, then we want to solve this differential equation so that we can model the charge as time goes on. All right, now we will learn all about how to solve such a differential equation. But when you do so, in this case, you have that the charge varies as a function of time according to 3 minus 3 e to the power of minus 4. Now that e to the power of minus 4 is what we would call exponential decay. And so in this situation, the charge comes up and it eventually approaches 3 as time goes on. Right? So this here is a plot of that function as t goes on. Okay, now the differential equation that we've just seen there is an example of a first order differential equation. And why, you ask? Well, the order of the derivative here is order 1, and that's the highest order derivative we have in that equation. Okay, now if you move over here on the right hand side of my screen, I'll give you some examples of orders of derivatives. So dy on dt, that's a first order derivative, which we can also write as y dash of t. A second order derivative is a rate of change of the rate of change. So d2y on dt squared, or you could write that y double dash of t, as a function of t. Okay, so there are two ways to write it. And then if we go higher, to higher order derivatives, we have, for example, a third order derivative, which we could say is d3y over dt cubed, or y triple dash of t. But you'll notice here that instead of putting 3 dashes, because that can get fairly cumbersome as you need more and more, right? So instead of doing that, what you can do is use a superscript, where you put a round bracket around your superscript and you put the number of times that y is to be differentiated. So in this case, y superscript 3, which of course you could write as y dash 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 of t, right? But it's more convenient here to put y superscript round brackets 3. Okay, now let's just look at an example of a first order differential equation. So for example, if we have dy on dt equals, let's just put 3y plus 5, okay? Now this is a first order differential equation because the order of the highest, the highest order of the derivative there is 1, right? We only need 1 dash there to describe that. So we'll say this is a first order ODE. Okay, now let's produce another example. How about here if I take all of this and square it? Okay, and then I suppose that this is equal to ty minus, say, 1 over y. Okay, ask yourself, what's the order of this differential equation? Well, ask yourself, what is the order of the derivative in there, and what's the highest order? Okay, you can see we've got a first order derivative, but it's being squared. Okay, even though it's being squared, this is still a first order derivative, okay? So we'll say this is a first order ODE. So I can just copy paste this. All right, because the highest order here is 1. All right, now let's take another example. What about this? Y double dash of t plus y dash of t minus 13 y of t equals 17. Okay, so there's a differential equation. It's an equation relating rates of change to other variables. And we could easily solve this, okay? In fact, we'll learn how to solve these equations, I think, in week 6. All right, now this is an example of a second order ODE because the highest order in the derivatives there is 2. So a second order ODE. Okay, and so on and so on. I hope you get the idea now. Okay, so let's move on. So next we see a simple description here of a rate of change that's constant. So this is the example I discussed earlier. So if we had water pouring out of a container at 3 liters per second, and that would be a constant absolute rate of change. Another example is if you're driving from, say, Petree to Sippy Downs at a constant rate of 100 kilometers per hour, right? We've described that in terms of the rate of change of the motion of the car. All right, and our aim would be to solve that differential equation. So to describe the position of your vehicle as dependent on how much time has elapsed. All right, so in that case, it would be a linear relationship when we solve that. Okay, so when a is positive, y of t is increasing, and so we have growth, right? And so you can see that here in the solution as well. If the coefficient of t here is positive, then y would be increasing as time goes on. But when a is negative, y would be decreasing. We would have a negative slope of this linear equation. So let's move on now to the next example. What if we have a constant relative rate of change? So what does that look like? It looks something like 1 on y dy on dt is equal to a constant. So this is a relative rate of change because in the numerator we have the rate of change, and then in the denominator we have the actual variable y. Okay, so we could rearrange that equation and write y dash of t is equal to k times y. So in this case, constant relative rate of change has k being constant and represents the relative rate of change. When k is positive, y of t is increasing, or y is increasing with respect to time. And when k is negative, y is decreasing with respect to time. Okay, so let's have a look at an example of this in the solution. When we solve this differential equation, and we'll learn how to do that very soon, we get y of t is equal to a constant times e to the power of kt. Now remember what e is, and I can just show you a little calculation here on the right-hand side of my screen. So I'll just put exp 1.0, right? Just to remind you what this is. So it's a constant, 2.71828, then we have different kinds of numbers. So it's not rational. So 459045 and so on. Okay, so that's what e is. And it's defined as a limit. But so when you take powers of this, you get your positive powers, you get positive growth, and it goes up very quickly. So let's just have a little look at a graph of this, which I have here. So there's some code here that you don't need to know. We just need to talk about the result. Okay, so here what I have is a plot of the general solution here for various values of a and k. So you can see it's initially set up with a is equal to 1. So that would be the relationship y is equal to e to the power of minus 3t, which is what you see here. And we'll talk soon about what the gray dashed line is and the vertical black line there. So what I want to do now is change the values of these. Okay, so let's first change the value of the constant, which you obtain actually from knowing what the initial value of y is. Okay, so when t is equal to 0, t is the horizontal axis here, we have y is equal to 1. So we in fact have a point 0, 1. Okay, so that's our initial value. So the solution then to the initial value problem, y dash of t is equal to ky, where y of 0 is equal to 1, it looks like this. This is the solution curve. Okay, but now suppose we change that initial value so we can see what happens. If I increase the value of a, now you can see the number here that I have increased a2, I'm keeping the exponent in the solution the same as minus 3. You can see we still have decay, right? So the value of y decays as time goes on down to well, down to 0, right? Okay. All right, so I'm increasing the value of a here, so up to 3, and I think I'll leave it there. So you can see what happens. It just brings the initial, we have the initial value being higher with a higher a value, but the long-term behavior of this is that the y value approaches 0 as time goes on. Okay, now let's bring that back and reset that constant. And now let's change the k value in this y equals a e to the kt. So I'll increase this now slightly. So you can see on the right hand side inside the box, you can see what I've changed the k value to. Now it's negative, so we have exponential decay. All right, but I will increase this slightly towards 0, and you can see it just makes that decay more slow, right? As I increase this towards 0, it makes that exponential decay more slow. Okay, now at a certain point we'll get to k equals 0, right? And at that point, when k is 0, it's essentially horizontal, right? So we have y is constant when k is equal to 0. Okay, now I have k positive, and now at this point we have exponential growth. All right, and so as I increase k, you can see it grows more rapidly at this point. Okay, now let's talk about what the dashed line is and the vertical line there. But let's go and reflect on this document for a moment. So we talked about the general solution. We've illustrated what that looks like. To find the doubling time when k is positive, we seek the time t such that y of t is equal to twice the initial value of y. Now remember, the initial value of y is just a. So if we substitute in what y is here to find that value of t, subbing in e to the kt in for y, and on the right hand side we have 2y of 0, which is 2 times a e to the power of 0, but e to the power of 0 is 1, so that's just 2a. Okay, now if we assume that a is non-zero, then we can divide throughout and eliminate the a, and what we end up with is e to the power of kt is 2. And we solve such an equation by taking a natural logarithm. Okay, so then I would get kt is equal to the natural logarithm of 2, and then I would divide by k to get t is equal to 1 over k times the natural logarithm of 2, which is approximately 0.7 over k. So this gives us the doubling time. All right, but what is the doubling time? It's the time required for the y value to double its original value. Okay, so that's what the height of that dashed line is. That's double the original value, or 2a. Right, and so what I've done next is drawn a vertical line down. So that vertical black line that you see there is the amount of time that's required for this to double. Okay? So how long does it take for the quantity y to double? All right, so we can view this again. Let's just initially keep a equal to 1 here, and we'll change. Actually, we want to start with y positive because that's what we're describing here, a doubling time, not a half time. Okay, so here we've got k is 0.385, and the initial value here is 1. So the double that is 2, and the time required in this case would be something like looks like 1.8, right? Which is where our vertical black line is. So 1.8, let's suppose it's in seconds, 1.8 seconds to double the y value. All right, so with that exponential growth, that's an important, I guess, way to sort of visualize what the exponential behavior is like. okay, because exponential behavior is difficult for humans to conceptualize, right? So it helps to know how long it takes to double. Okay, all right, next let's consider half-life. So if you have, let's say somewhere in England, some Roman stuff might have been discovered in a farm. Okay, now you might want to know how old it is, so you can decide, oh, is it Roman or is it something else? So there's something called carbon-14. It's an isotope of carbon that decays at a particular rate into a different form. Okay, so at a given time, you could measure how much carbon-14 is in there. And thereby measure how old the organic compound is that you're measuring. So you want to know what the half-life is and use that half-life to measure how old it is. Okay, so half-life is the amount of time required. Now this is for K negative, so let's scroll back to a point where we've got K negative in our diagram. So the amount of time required for the Y quantity to be half of what it originally was. Okay, so here if we started with 1, half of that would be a half. How much time is required for that particular K value? Here we've got K is minus 0.835. Okay, and so in this case, let's imagine the T is in seconds here. This looks like something like a little bit more than 0.8 seconds to have half of the original value. But if I take the K value back towards minus 3, for example, you can see that the decay is more rapid here, so it's much more quick until that's half. Now let's increase the A value. All right, so you can see as I increase the A value, that does not affect the half-life. All right, because remember, this is relative to the original value. So how long does it take to halve? Okay, so that's not dependent on the original value or the A value. It's dependent on the rate, or it's dependent on the K value, right? All right, so for example, it has been said that after drinking a cup of coffee, it takes about 2 or 3 hours for your body to eliminate half of the caffeine from your system. So think about this. If you get up in the morning and have a cup of coffee, you really don't want to have that too late in the day because you want sufficient time to elapse that you have virtually 0 caffeine in your system before you go to bed again, right? So let's suppose the half-life is 3 hours. Okay, so you have a cup of coffee at 8 a.m. So by 11 a.m. you have half of that caffeine in your system. And then another 3 hours is what, 2 p.m. So you've got, by 2 p.m., you've got about a quarter of that caffeine in your system. Okay, by 5 p.m., an eighth, and so on, right? So by the time you go to bed, you don't want to have more than, say, 1/16 of that caffeine still in your system, right? Because you might get insomnia. Okay, other drugs have different half-lives, right? Similar behavior, exponential decay, but different half-lives. And remember what that corresponds to. It's a different K value. So if we scroll back up here, so a different drug would have a different K value in this rate of change up here, so leading to a different half-life. So nicotine is said to have a half-life of approximately 2 hours. Blood alcohol concentration decays linearly, apparently. So most likely a different differential equation. Okay, now let's move on and talk about equilibrium. So let P of T be a concentration at time T of a poisonous toxin in a river. Let's assume that sunlight breaks that toxin down according to this relationship. The rate at which the toxin breaks down is minus a positive constant. So this is a negative number times P. So in other words, the rate depends on how much toxin is in that river. Okay, but a nearby activity, suppose, adds toxin to the river at a constant rate, A, let's assume that's positive, so that we have, in reality, the rate at which the toxin breaks down is equal to minus Cp plus A. So more is being added to it. We can consider the equation qualitatively, right? So that is, without solving this first, we can know something about it by consideration of the equilibrium or steady state solution or solutions, because there could be multiple. In other words, what solution is obtained when we have a zero rate of change? That's not dependent on t. So in other words, not locally. And I'll show you an example of that soon, of the distinction. So for the equation that we just saw, is there an equilibrium solution? Okay, so let's consider what happens when we put in dp on dt is equal to 0. So we're seeking an equilibrium solution, p subscript eq for equilibrium, such that that rate is equal to 0. So basically we sub in 0 for the left-hand side of this equation here, and we solve for p. Okay, so we can take the a over to the right-hand side here and then divide by minus c. So we have minus a over minus c, which is a over c. So our equilibrium value of p is a over c. So for example, if c is equal to 1 and a is 2, then the ODE, p dash of t is minus p plus 2, has the unique equilibrium solution p equal to 2. And this tells us the long-term behavior of that system involving the toxin. Okay, so does it tend to a concentration of 2, or is it tending away from that, right? All right, so see figure 2. So let's have a look. So figure 2 is down here. So in this case, this will be stable, okay, mainly because that ratio, because a over c is positive, so trajectories will be tending towards this. Now you see several curves here with arrows on them. They point towards that line p equal to 2. Okay, now each of those is a solution to that differential equation, because remember, in a general solution you have solutions for basically any initial value that you have, right? So you have several solutions. Now an initial value you can think of as a point. Say, suppose when t is equal to 1, you have a concentration of p equal to 2.5. Okay, so that's roughly where my mouse is. You might have a point. Okay, so that would be an initial value, and then that would fix a particular trajectory. And so following along here, you would tend down towards the concentration p is 2. However, if on the other hand you had an initial value of, say, when t is equal to 3, p is equal to 1/2, so roughly right in here where my mouse is, then you follow a trajectory that starts there, and you see in this case it tends up towards the concentration p is 2. Right, so essentially with the equilibrium solution we know that since it's stable, all trajectories, no matter where they're starting, will tend towards that concentration p equals 2. And so we know the long-term behavior of the system without even solving the differential equation. However, in this case, it's easy enough to do, right? So we can actually solve that differential equation. All right, so let's have a look now at stability, and how do we classify the stability of an equilibrium solution to a differential equation. All right, so we could have stable equilibrium in which trajectories tend towards a particular value, or an unstable equilibrium. Now here you can see a little drawing of a pencil under gravity, but I can do the same thing here with my clipboard and my pen. Okay, so I can try to balance this pen on the tip. Okay, now you could describe this situation with the differential equation, but you see, as soon as I let go, it falls one direction or another, right? It does not want to stay at the equilibrium that is, vertical balancing. It wants to just fall one direction or another. So if you have a differential equation with an unstable equilibrium, then trajectories will tend away from that equilibrium solution as time goes on. I will point out that an equilibrium solution is an actual solution to the differential equation. Right? So if you check this one here, p dash of t is equal to minus p plus 2. The equilibrium there is p equals 2, but you can see if p is equal to 2, and we differentiate, so the derivative of p is equal to 0, okay, so that satisfies this differential equation because we have 0 on the left and minus 2 plus 2 on the right, so 0 equals 0, and hence it satisfies that. So equilibrium solutions themselves are trajectories, right? So it would be possible to balance a pen perfectly on its tip, right? If there were not, outside perturbations there, like, molecules bouncing into it and pushing this away, right? It is an actual solution to that system, but it's an unstable one. Okay, so for any differential equation which can be written in the form dp on dt is equal to f of p, so in other words a function of p, the stability of the solution can be determined from a sketch or by checking the sign of the slope. So you simply differentiate this function with respect to p and then sub in that equilibrium solution that you found earlier. Okay, if f dash of p equilibrium is positive, then we can deduce that the equilibrium is unstable. If f dash of p equilibrium is negative, then we can deduce that the equilibrium is stable. Okay, so let's go up and have a look here. So here's our function of p, in this case that we found a stable equilibrium, is minus p plus 2. Now if we differentiate that again, we get minus 1. Okay, minus 1 is negative. That tells us that this equilibrium here is stable without drawing the slope field there. Okay, whereas this one up here is unstable. Now I don't have an example of that. I'm sure we'll encounter one. Okay, but there are other ways to do this as well. So if you just take a particular value, like you guess an initial value, and then you look at the sign of the slope, you can tell that it's going away from the equilibrium, right? So this is not the only way to do it. And other ways come in handy when you have what we would call a semi-stable equilibrium. And a semi-stable equilibrium is when you have trajectories on one side of the equilibrium tending away, and on the other side of the equilibrium they tend towards. But we'll see an example of that soon. Okay, so this is a little diagram that describes this situation here on the sign of f dash of p subscript eq. So we have a description here of a negative slope, and the trajectories tend towards in that case. Okay, now let's have a look at an example. Consider the equilibrium solutions of to the logistic equation for population growth. Okay, so in some cases you can describe the growth of population of a particular collection of, say, animals or people or whatever. You can describe the rate of change of that population as depending on the population and other factors. Okay, so let's suppose k and a are constants. So if we're looking here for equilibrium solutions, then we want to sub in dp on dt is equal to 0. So in this case we have this equation, kp times 1 minus p on a is equal to 0. And we want to solve for all such p that satisfy that equation to get the equilibrium solutions. Okay, so this one has equilibrium solutions p equals 0 and p equals a. So if we assume now that A and K are positive, let's consider some trajectories that start with initial population negative. Now this is not a realistic example, right? But it does sort of illustrate theoretically, right? So you can't start with a negative population. That's just ridiculous. But anyway, abstractly here, it's descriptive enough. Okay, so if we start with population negative, we see then that 1 minus p over a is positive and kp is negative. So looking at this, the product of those two then is negative. So dp on dt is negative in that case. So on that side of the equilibrium, p equals 0, the slope is negative. So that tells us that trajectories move away. So the arrows go left to right in the diagrams, right? So they move away from that equilibrium p equals 0. So next, let's consider trajectories that start with an initial value p of 0 between 0 and a. Remember, a is positive here. So this is a positive one. So this is a more realistic example. So in this case, we have k times p is positive and a minus p is positive, so that 1 minus p on a is positive, and hence the product of kp and 1 minus p on a is positive. So we see then that dp on dt is positive in that case. So that in that case, trajectories have a positive slope and they're moving away from the equilibrium p equals 0. So that alone tells us that the equilibrium is unstable at p equals 0, right? So the population would not like to remain at a 0 population, right? That's an unstable equilibrium. Okay, so finally let's look in a different region here. If p of 0 is positive, so if our initial population is positive, then what we have is k times p is positive and a minus p is negative. Okay, that's just taking this over to this side. So a minus p is negative. So we deduce that 1 minus p over a is negative. And hence we see that dp on dt is negative in this case. All right, so on the other side of that equilibrium, so if we start above the equilibrium p is equal to a, then the trajectories will move down towards p equals a because we have a negative slope. So in other words, trajectories that start with p positive approach the equilibrium p equals a, showing that that one's a stable equilibrium. Okay, so this tells us straight away that the population will tend towards the constant p equals a. And that's without even solving that differential equation. Okay, moving on. Now let's do this using the f of p approach. So alternatively, if we let f of p be equal to the right-hand side of our differential equation, kp 1 minus p on a, and we differentiate that, so we'll do so with the product rule of differentiation, we get k times 1 minus p on a, take kp on a. Okay, now we substitute in to this function our two equilibrium solutions. We had 0, so subbing in p is 0 into here. We have k times 1 and then minus 0. So we just get k for that, and we know since we assumed originally that k was positive, so f dash of 0 is positive in that case. All right, remember that tells us again that the equilibrium is unstable. The equilibrium p equals 0 is an unstable equilibrium. Okay, now let's do the same thing with p equals a. Hang on, I gotta go. Yeah, my cat found the neighbor cat and got very upset. Okay, where were we? So if we sub in p equals a into this function f dash, so what we have then is p over a is 1, so 1 minus 1 is 0. Okay, and then on this part of it we have ka over a, so minus k. So we get f dash of a is equal to minus k, but that's negative since we assumed k was positive. All right, so this tells us that that equilibrium p is equal to a is is a stable equilibrium, right? So we've got two approaches here to determine that one is unstable and the other is stable. Okay, now if we were to solve that differential equation, we would get the solution, this is the general solution, P of t is equal to lowercase a times some constant a of integration times e to the kt all over a e to the kt minus 1. Okay, now that constant a of integration, the uppercase a there, depends on the initial condition, and you can find that if you know the initial condition to get a particular curve that models that population as time goes on. Okay, now I'll just show you those trajectories. So this line p equals 0, that was one equilibrium solution, and we know that it's totally unrealistic to have a negative population. So you can more or less discard what's under that t-axis there. Okay, so this population equals 0 is a solution to the differential equation, but it's unstable. So you most likely do not have a 0 population there if you had an original population. Okay, so if your initial condition is somewhere between 0 and a, here I've got an a value equal to 1, just for example. So if it starts out between 0 and 1, your trajectories here will tend towards a, right? Because that is a stable equilibrium. So that's what that black curve is. It's just a particular choice of uppercase A here in this solution curve, right? That corresponds to a particular initial value. Now, if you were to have an initial population that's above that equilibrium, then they would tend, the population over time would tend towards that equilibrium solution. So we would have a decline in population until you get very close to the equilibrium solution. All right, so let's move on now. So here's a more, I guess, theoretical example to show you the difference between an equilibrium solution and just a local y dash equals 0 case. Okay, so if we consider the ODE, y dash is equal to y times y plus 2 times y minus t squared, and we look for equilibrium solutions. So we solve the equation y dash is equal to 0, and we get multiple solutions. We could have y is equal to 0, y is equal to minus 2, and y is equal to t squared. Each of those give y dash is 0. Okay, so y equals 0 and y equals minus 2 are equilibrium solutions. However, y is equal to t squared is not an equilibrium solution because that gives you a derivative equal to 0 only temporarily. So have a look here at the diagram of various trajectories in blue, right? So you can see if I had an initial value that was, say, 0, so t equals 0 and y is equal to, say, 1. Okay, it would start out going up, and then when at the point where y is equal to t squared, it would turn around and go back down. Okay, now I've highlighted that equation y equal t squared in red, so you can see that's the point where trajectories turn around. The red is not a trajectory itself, it just shows us where these trajectories turn around. So we don't want to identify this as an equilibrium solution, it's only a temporary turnaround, right? The equilibrium solutions are actual solutions to the differential equation for all time. Okay, and they tell you what happens to various trajectories. In this case, we have a stable equilibrium at 0, and trajectories tend towards that solution. Whereas down here at y equals minus 2, that solution is unstable, and trajectories will tend away from it. Okay. All right, let's move on to the question of do solutions always exist to initial value problems? And the answer is no, not in general. So here we have the existence and uniqueness theorem, which can be presented in various forms. So if you want to see another form, just go ahead and have a look through any of the books. At the back of this little booklet, I've got a collection of some of the books that I think are relevant for you. Right, so you go have a look through some of these and others for another presentation of the existence and uniqueness theorem. So we'll go back to it here on page 12. Okay, so the initial value problem, so IVP for short. So an initial value problem is a differential equation where you know some particular initial value to fix a particular trajectory. Okay, so the initial value problem with point t0, y0, where f is a function, has a unique solution near the point t0, y0 if f and the partial derivatives with respect to each of the letters are continuous and f is differentiable. Okay, so continuous means I don't need to lift my pen to draw it. And differentiable means that the derivative exists and is not ambiguous. Okay, now if we go down here to this little curve, at this point 0, 0 in this folium of Descartes, we have an ambiguous derivative there at 0, 0, right? Because at the point 0, 0, you ask, what is the slope of this curve, right? It's not exactly one number, right? It's because we have two slopes at the point 0, 0. So that's an example of a non-differentiable curve at the point 0, 0. So we require our curves to be differentiable and continuous. Okay, so a solution exists in some little region provided these things hold. Okay, solution curves do not cross themselves or each other. So that's important because you know based on equilibrium solutions that your trajectories are not going to cross that equilibrium solution, right? They never cross the equilibrium solution because that equilibrium is an actual trajectory of the ODE. It's an actual solution of the ODE. So they don't cross that, which is important, right? Especially when you're using numerical approaches to solve your differential equation. Okay, let's have a look at a little example here of how qualitative analysis can be useful. Consider the initial value problem y dash of t is 5 times y minus 2, and the initial value here is when t is equal to 1, y is equal to 1. Okay, so the question, do we have y of t less than 2 for all t greater than 1? Okay, now let's have a look at our initial point. We've got when t is 1, y is 1, so that's a point that I've got highlighted down here in black. Okay, and the corresponding trajectory heads down away from the equilibrium. So we know there's an equilibrium at y equal 2. We can see that just by solving for when y dash is 0. So the point is below that, and we know that this is unstable, so it tends away. All right, so yes, we do have y of t less than 2 for all time greater than 1. So it's useful in telling us the long-term behavior of the particular trajectory without actually solving the differential equation. Okay, now let's have a look at a semi-stable example that's neither stable nor unstable. Okay, have a look at this diagram. Trajectories that are above the equilibrium y equals 0 tend away from that, whereas trajectories that start off below y is 0 tend towards. And so we call this a semi-stable example, right? So an example of this is y dash equals 2y squared, and it's all because of that square. um, that makes that happen. So if you had an even power, you would have a semi-stable equilibrium.